Good morning, students. Welcome back to digital signal processing class. In the previous class, we have discussed the concepts of Randolph, what's a noise, what is the quantization, how do we get the errors, how do we get floating point, how do we get the fixed point representation. These all concepts we have covered in the previous class, right? In today's class, we are going to concern the last topic of your unit 3. That's nothing but comparison between your FIR and IIR kind of filtering. So basically, what is FIR stands for? Finite impulse response filter. What about IIR stands for? Infinite impulse invariant response. That is invariant impulse response, you can say. Whereas FIR can be designed by considering what? By considering windowing technique, in which your infinite number of samples we are truncating into a finite number of samples. Why? Because we want to get less errors. That should be more stable, more flexible to design the kind of filtering, right? Whereas in IIR, it is going to use the infinite number of samples. It has more number of noise will be there because there is a number of samples is increasing. It is infinite. Lower limit, upper limit, both are unknown for us. Because of that reason, we can say IIR is quite, we can consider to be the less flexible. That should not be properly stable, because as compared to FIR, if you see some part of it, it is not having that kind of good features when we are comparing FIR with IIR. Let us see the comparison. So first comparison, we are saying FIR filter is going to design the perfectly linear phase kind of filters. What is a perfectly linear phase? I have explained you linear phase kind of filtering, right? Linear phase means the input and output response should be the linear in nature. So FIR filtering by using all kind of windowing techniques, if you consider Hamming window, Hanning window, Kaiser window, Blackman window, any kind of windowing technique, all windowing technique make the filter into linear in phase. So because of that particular reason, we say that your finite impulse response filtering always in linear, and it is perfect linear in nature, whereas IIR filtering we can consider to be the don't have that much of linearity, because here windowing techniques we won't use. Here we use all kind of filter, low pass, high pass, band stop, band pass filters, all kind of filters we will consider, and we will design by using bilinear transformation or impulse invariant method, right? So what is that bilinear transformation means? When you want to convert S domain to your Z domain, we'll multiply with the factor 1 minus Z power minus 1 by 1 plus Z power minus 1 into 2 by T. This we are using for bilinear. So this we are doing for bilinear transformation. So for bilinear transformation, we are going to use this particular factor. Whereas for impulse invariant response, what we will use, students? So impulse, to just make you recall of that concepts. So when you want to convert your S domain to Z domain, we'll multiply with the factor 1 minus e power minus p of t into Z power minus 1, right? This is for impulse invariant response. So by using this impulse invariant response, we'll multiply those factors. So by converting into the IIR filtering, this will be useful whenever we want to design the filters of your IIR kind of filters. In that IIR kind of filters, we mostly consider the filtering response. So whenever we want to see any kind of filter response, we mainly concern with these factors. So in that, we'll either use your Chebyshev kind of concepts, or we'll use Chebyshev type 1, type 2 or Butterworth kind of filtering, right? So we have seen that also, Butterworth and Chebyshev all kind of filterings that will be useful for IIR. In IIR, Butterworth analog or digital will use, or Chebyshev type 1, type 2 analog or digital will use. Out of that, because of all those kinds of concepts, we can say that IIR don't have that kind of linearly phased response or linear phase response. Next, it can be used to design recursive and non-recursive kind of filtering. The term recursive and non-recursive comes into picture when you want to design and you want to find out the response of the filter. So when you want to design these kind of FIR kind of filtering, the most important concept is this recursive and non-recursive. So it is useful for both recursive also as well as non-recursive. Whereas your IIR filter only useful for recursive kind of filtering only. It is not used for non-recursive. Okay, so this is only the reason we are proceeding with FIR. Here it is flexible to design and control all kind of magnitude response. This is the magnitude. Okay, magnitude response. Okay, it is having the control over the magnitude response, whereas it has less control over the magnitude response, and it is limited to specific kind of filtering. Why it is limited? Because Butterworth approach is different as compared to Chebyshev, and if you are using low pass, that designing is different. If you are using high pass, that designing is different. So that's why it is less flexible. So less flexible, and it is limited to specific kind of filters. That is a third point I said. And in the fourth, the last point, what I'm saying, error due to the Randolph's noise are less because of the feedback is not used. Here we are not considering any kind of feedbacks, and it is quite easy for us to design these kind of filtering, and it is having less number of errors, right? Whereas IIR has more round of errors, because here we are not truncating the sequence. Truncating in the sense we are not limiting the sequence, we are not finding the sequence into a particular domain. So because of this reason, we say that IIR has more round of noise as compared to FIR. You can write one more point, that these filters can be designed by using, FIR can be designed by using the filters. You write down the filters, whatever filters we are using. What are the windowing techniques? This is useful for windowing techniques. This is useful for using the approximation methods. Butterworth approximation, Chebyshev approximation. So by using that, you can say that these are having less number of noise because of the truncation, because of the limited of the response. That is nothing but finite impulse response, whereas here infinite impulse response here is there. That's the reason you can write multiple points by seeing the main. These are the main points you can write as per the question requirement. If it is asked for LEQ, you can have to write at least 10 points. Okay, so you have to mention, even you can write the formulas. You write how can you say you is a recursive and non-recursive by giving the formula to it, and you write down all the kind of parameters which we are writing for FIR and which we are writing for IIR kind of filtering. So note down these points and write by your own all the points which I have said orally. I have written less points. When I am explaining, I said lot of points for this. Okay, so make a note and write. This is in your running notes. So students, we are going to start the next unit 4. So unit 4 is quite simple. It is going to finish in 3 to 4 lectures. Only the sampling things we do have. The unit 4, the name is nothing but multi-rate signal processing. Okay, so first thing we do have concept of decimation, then we do have a concept of, second one is interpolation, and where we use this multi-rate digital signal processing, multi-rate DSP you can write. Okay, so in unit 4 we are using the concept of DSP. So here we are completely concerned with your multi-rate DSP. So basically what is multi-rate DSP? It is using two concepts. In one is upsampling, that is interpolation, and another is a downsampling, that is called decimation. So why we need to use this upsampling and why there is need to take the downsampling? So basically what is the meaning of sampling? We have already seen, right? So whenever we had a continuous kind of response we have to make into discrete form by using the sampling theorem. It consists of quantizations and it also have the samples, right? Sampler and quantizer, but both combiningly considered to be the sampler, right? So basically why we use this decimation and interpolation, because we want to make, since I'm saying multi-rate, it is not having a single rate, it is using multi-rate DSP. It varies the sampling rates based upon the processing, what kind of processing you're going to deals with. So when you want to design these kind of sampling rates, for doing this we have to sometime decimate it. If it's increasing the cutoff region, it is increasing the not cutoff region, I'm saying if it is increasing the band of frequency, after that it is increasing beyond it, then we have to decrease the sampling rate. If it is lesser, then we have to increase the sampling rate. This will be useful, sampling rates and all those things, it will be useful in various domain. In medicine field it is used, in medicine field we use for ECG in ECG, in EEG, for these kind of scanning, all those things we are going for this multi-rate DSP. And even in audio signal processing, for audio signal processing also this is particularly useful. Even in the other countries like Europe and all those things, when they want to go for telecasting any particular video conferencing or any other thing, when they had particular conference or all those things, they have to go for multi-rate DSP, because they keep on changing the rate of that particular signal. People needs to first sample that particular rate into by using the filters. So those things, there are a lot of applications, and in details of this decimation interpolations and its block diagram we will see in the next class. So before ending with this thing, you first see where this multi-rate DSP useful. It is used for high quality data acquisition and storage system. Means when data is increasing beyond that particular value, for that particular thing, it is also used by using multi-rate DSP. Okay. Next thing, in audio signal processing, for example, a CD is sampled at 44.1 kilohertz, but data, whatever the digital audio tape is there, is sampled at 48 kilohertz. See, these two are having different values, 48 here 44. So for converting this data into particular value, this multi-rate signal processing is useful. Next application, in video, PAL and NTSC run a different samples rate. So for that, we have to watch an American program in Europe. 1:2 sampling rate converters, means when you want to see the American programs in Europe, you have to first go for sampling rate converters. Then only it will be easy for you to see, because one will use PAL, another will use NTSC kind of sampling rates. Next one, it is speech processing also is useful for reducing the space and transmitting rate of the speech data. So whenever you want to go for data increasing and all those things, for speech processing, there is a speech processing techniques we had. For that also it is going to be useful. In trans multiplexer it is useful, because we already know multiplexer means multi inputs will give and we'll try to get one of the output by considering the select inputs. In narrow band filtering for fetal ECGs and EEGs, these is useful. So these are the application of it.